All right, here we go. So a strong base, just like strong acids, they completely dissociate, or they completely ionize when we put them into solution. So again, the way that that works with a strong base, NaOH, okay, we get complete dissociation between the metal ion and the hydroxide ion. Okay, so when we're looking at strong bases, the generic formula for that, so with acids, it's HA. With bases, we do MOH. The M stands for the metal, so either a group 1 metal or a heavy group 2. And so we write that as M plus, meaning the metal ion, plus a hydroxide ion. And so when we have a strong base, this ionization happens completely, right? They lose all of their OH at the same time. So again, with acids, we talk about them losing their hydrogens one at a time. So if we have H2SO4, when it ionizes, we get H plus HSO4 minus. So one hydrogen at a time. When we look at a base, if we have, for example, barium hydroxide, which is BaOH2, both of those hydroxide ions are going to hop off at the same time, leaving our metal ion by itself. Okay. So that's kind of the difference between what acids do and bases do. So they lose all their OH at the same time. So the concentration is equal to the concentration of the strong base times the number of OH groups. So that's something that we have to think about. What that means is if we have barium hydroxide, okay, and its concentration is 0.0 molar. When we produce this, right, it dissociates to give us Ba plus 2 OH ions, right? So if the concentration of barium hydroxide is 2 molar, what is going to be our concentration of OH ions? So if the concentration of barium hydroxide is 2.0, what's going to be our concentration of OH? Ami, what do you think?
It's going to be 4 molarity.
Yep, it would be 4 molar. And the reason for that is that for every 1 mole of barium hydroxide, we're producing 2 moles of hydroxide ions. Okay, so because this is a 1 to 2 relationship, what we would need to do is for every 1 barium hydroxide, that's 2 OH ions that are being produced. So 2 times 2 would give us a molarity of 4. Does that make sense, guys? That's a little bit different from when we talk about a strong acid, right? With a strong acid, this is a 1-to-1 relationship, whereas bases sometimes, not always, but sometimes can be a 1-to-2 relationship. And that's what's different with bases, is occasionally we have to multiply by a coefficient of 2. That never happens with acids. Acids are always a 1-to-1, and that's because they just lose 1 hydrogen ion at a time, whereas bases lose all their hydroxides all at once. Okay. Anybody need another minute with this? Cool. All right, so here's an example. It says find the pH of our sodium hydroxide solution. So it wants us to find the pH. So if we take a look at this, we have concentration of NaOH. NaOH is going to dissociate into Na plus and OH minus. So what's nice about this is it's all 1-to-1-to-1, only 1 hydroxide. So we have the concentration of NaOH is 5 times 10 to the negative 2. So what is going to be our concentration of OH in this solution? Connor, what's going to be the concentration of the OH?
It's going to be the same, right?
It's going to be absolutely the same because this is a 1-to-1 relationship, so we don't have to multiply, or we're going to be multiplying it by 1, so it would be the same. Yep. So 5.0 times 10 to the negative 2nd molarity. Okay. So this is equal to our concentration of OH minus. Okay. That's what we got right there. That's not 10. There you go. So we've got this concentration for OH. What this is asking for is for us to find what? What are we trying to find in this particular calculation? Drew, what are we looking for?
The pH.
Yeah, we're trying to find the pH. Okay. So in order to go from concentration of hydroxide ions to pH, we can't do that in one step. That's going to be a 2-step conversion. So what you're going to want to look at is your AP equation sheet. That's going to kind of let you know what you can do with the numbers that we have here. Okay. So if I take a look here, it shows me that pH plus POH is 14. It also tells me that POH is equal to the negative log of the hydrogen ion concentration. So we can use these two equations to get us where we need to go. So what is going to be our first step? What are we going to do with this hydrogen ion concentration? Olivia, what are we going to do?
Convert it to the O to the H, right? Yep.
To the what?
To H. So you're
To
going
H?
to use
What do you mean by H? Oh, to the H concentration?
Yeah.
Yeah, we can absolutely do that. What equation are we going to use to make that happen?
The 14 equals pH plus POH.
So that's for pH and POH, and we don't have either of those. We have a hydroxide ion concentration. Okay.
Okay.
So if we want to use this pH POH equation, what do we need to do to our concentration of OH first? What do we have to do?
Negative log of the concentration to find the OH. Okay.
Yeah, that's exactly what we need to do. There is another way around. So what I thought you were referring to is this equation up here. Kw is equal to the concentration of H plus times the concentration of OH minus equals 1 times 10 to the negative 14th. So we could have taken our hydroxide ion concentration and converted it to H plus and then done the pH. But I think the path that you just identified is actually mathematically a little easier. So yeah, the first step we need to do is figure out what our POH is. And so we're going to do negative log, like you said. And just like we were converting concentration of H plus to pH, we can get POH. So negative log, and then we're going to take that concentration of our OH, which was 5.0 times 10 to the negative 2nd. And we can plop that into our calculator. Okay. So we can type that in, and that would be negative log, and then we type 5.0 second E negative 2 and parentheses. And so we get 1.301. So 1.30 is going to be equal to my POH, right? Because remember, P stands for negative log, okay? So we just took the negative log of the OH concentration to get POH. Now, Olivia, what did you say would be the next step?
So because we have the 14 and the pH plus 1.3, we can subtract 1.3 from 14 and get pH.
Yes, a little bit of algebra to rearrange that. We can say 14 minus the POH will give us our pH. So our POH was 1.30, and that's going to be equal to my pH, which was the final answer that we were looking for. So 14 minus 1.3 would give us 12.7 is our pH, and this would be our final answer that we were looking for by doing this problem. Okay, any questions on this? So the mechanics of this last part, going from concentration of OH to POH to pH, is something that you're going to have to do over and over again when we're trying to figure out the pH of a weak base as well. So anytime you're trying to find the solution, or sorry, the pH of a basic solution, you're going to take your hydroxide ion concentration, get to POH, and then you can easily get to your pH by just subtracting. Okay, so that's our example there. Okay, another example, in this particular case, we've got more than one hydroxide ion. All right, so what would be the ionization equation for this, or the dissociation equation? What would we write for this? Emily Krulikowski, what would that be? What would that look like? The dissociation equation here for our calcium hydroxide.
Would it be 1CaOH2 turns into one Ca plus 2 OH negative?
Yeah, so Ca would be 2 plus how many hydroxides?
2.
Yep. 2 OH minus. So yeah, we've got a 1 to 2 relationship here with our hydroxide. So the concentration of calcium hydroxide was 3.0 molar. So what is going to be our concentration of our hydroxide? What would we need to do? So Emily, what would we get?
We would get 6 molars.
Yep, we'd get 6 molar, right? Again, we would multiply this by the fact that for every 1 calcium hydroxide, we produce 2 hydroxide ions. So that would give us a concentration of 6.0 molar OH. Okay, so now it says find the POH. So we're trying to find the POH again. Very similar to what we did last time. So what are our steps? What are we going to do? Ethan, how are we going to go from 6 molar OH to pH? What are we going to do?
The negative log,
Negative log of what?
the concentration.
And what's my concentration?
The concentration is going to be the 6.
Yep. Okay. So we're going to take the negative log of 6. And so when we do that, negative log 6, we hit enter. And when we do that, the negative log of 6 is equal to negative 0.778. So that is my POH. So now we have POH. What's the next thing that we need to do? What's our final step? Annika, what's the next thing we're going to do?
You would do 14 minus the POH to get the pH.
So 14 minus the POH, and the POH is negative 0.778. So minus a negative is the same thing as adding, right? So we would get 14.778 is our pH. If we're looking at significant figures, that's 2 sig figs. So then we'd actually round this to 14.78. Something weird with significant figures and pH. With pH, the numbers in front of the decimal don't count into our total of significant figures. We only look at the decimals behind. So we had 2 significant figures in our starting value. So we'd keep 2 decimal places on this pH as our final answer. All right, there we go. So that's how we do strong bases. All right, so some bases don't have OH, okay? Remember, we revised our definition of a base to be anything that would accept a hydrogen. So anything that a hydrogen will attach to, we would consider a base. So a classic example of a base that doesn't have hydroxide on it is ammonia, okay? Ammonia, like the ingredient in window cleaner. So ammonia, NH3, when we put this into water, here's what's happening. So NH3 is my base. water is going to act as my acid. And what we get as a result is the hydrogen from water is going to get transferred to my ammonia and form what's called ammonium, which is NH4+. And when we do that, when a hydrogen leaves water, it forms hydroxide. So even though there's no OH in the base itself, it still produces OH ions by stealing a hydrogen from the water. Okay, so if you label this, this is my base, okay, and water is my acid. And the reason why water is the acid is it gave up a hydrogen. The reason why NH3 is a base is because it gained a hydrogen. And so if this is my base, over here, it's going to be its conjugate acid. And this is going to be the conjugate base to my acid. Okay. So again, bases don't have to have an OH attached to them. What bases will do by accepting a hydrogen from water will produce hydroxide ions. So we can still figure out the concentration of OH in a solution. To do this, to figure out how much OH we're going to get when we put the base into the water, we're going to have to do an equilibrium expression. Hi, Aiden. Welcome. And so when we're dealing with bases, instead of using a Ka, what we're going to need in order to figure this out is we're going to need a Kb. Okay, so the Kb is going to tell us our expression. That's okay, Aiden, no worries, it happens. So our equilibrium expression in this case, we'd have the concentration of NH4 times the concentration of OH minus over the concentration of our base. Okay. So we're going to do the exact same steps as we did with the weak acid, this time with the weak base. And instead of setting our equilibrium expression equal to Ka, we would set our equilibrium expression to Kb because we're dealing with a base. And that's all the B stands for, is the equilibrium constant of a base, whereas Ka is the equilibrium constant of an acid. Okay. All right. So let's take a look at the steps for solving. So the first thing you need to do is look up the Kb value, or convert PKB to Kb. We're going to write the dissociation equation for the base. We're going to write the equilibrium expression. We're going to set up an ice table. We'll solve for our concentration of OH minus. And then we're going to do all those steps we just did with the strong bases. We're going to find the concentration of OH. And then once we do that, we'll convert it to POH. And then we'll do 14 minus the POH to get to pH. So it's really just only one step further than what we're doing with a weak acid. With a weak acid, we get the concentration of H+ right away, and we can just take the negative log and we have our pH and we're done. What's different here is because we're going to have concentration, so X is going to equal the concentration of OH minus ions. Then we're going to have to then convert to POH and then do 14 minus POH to get to pH. So really, this step right here is the only extra step that we have compared to what we were doing before. So if you were catching on to how to do, or to figure out the pH of a weak acid, figuring out the pH of a weak base is only one additional step, but the setup is the same. If you were struggling with that the other day, hopefully by doing a few more of these base calculations, it'll also help you with your weak acid calculations because it's all the kind of same mechanics. All right, so let's do our first example problem. It says, find the pH of a weak base. So find the pH of 15 molar NH3, and its Kb is 1.8 times 10 to the negative fifth. So here are all the steps that we need to go ahead and follow, right? We're going to need to write the dissociation equation for the base. We're going to write the equilibrium expression. We're going to set up an ICE table. We're going to solve for OH. Then we're going to get our POH, and then we're going to go to pH. Those are going to be the steps that we're going to follow. So let's write our our dissociation equation. Remember that we have to put this in a solution of water. So how would we set this up? What would we write for our dissociation? So Pamela, what would I do with this? How would I write the dissociation?
So we will have to start with an H3
Uh-huh.
associated to
So we need to make sure that we put it in a solution of water, H2O. So when we put that NH3 in the water, so this is going to be aqueous and water is going to be our liquid, what's going to happen?
So we're gonna have to get OH negative plus NH4.
Yeah. So what makes this guy a base is the fact that it's going to gain a hydrogen. So yep, we're going to get NH4, and that's going to have a positive 1 charge because it's gaining a positive hydrogen. And then we're going to be left with OH minus, just like you said. Okay. So that's our dissociation equation. That's step 1, right? So write the dissociation equation. We've done that. Next thing it says, write the equilibrium expression. So Connor, what is going to be the equilibrium expression for this?
Is that where you say like the concentrations and stuff?
Yep.
KB equals NH4 plus and then OH over NH3.
Good. Perfect. Okay. So there's our equilibrium expression. So we've done that. So then the next thing we need to do is set up an ICE table. Okay. We've set up ICE tables millions of times before. It's not any different. So we have to write down what is our initial. So let's fill out our initial line. So what is going to be our initial line that we're going to put in here? Emily Augustin, what is going to be my initial line?
15 molarity for NH3.
Yeah.
And then we don't put anything for H2O because it's a liquid.
Perfect. You even gave me the Y. And then what are these going to be?
0.
Why are they 0 to start?
Because they haven't produced anything. It's the initial.
Yep, exactly. No dissociation has happened initially. And then Emily, what is going to be the change?
Minus X for NH3. And then plus X for the products NH4 plus and OH minus.
Perfect. Okay, and then we're going to write what's going down at equilibrium. So here we're going to have 15 minus X, and then X and X. Good. So now that we have this, what's our next step? What's the next thing that we're going to need to do? What's the next step here? So Drew, what's the next step now that I have the equilibrium? So Emily set us up with our ICE table, which is awesome, right? So we got that taken care of. What's the next step? So it says solve for OH concentration. How are we going to do that, Drew?
Put it into the equation.
So we're going to put it into the equation. So Connor set up our equilibrium expression for us. And KB we have up above here is 1.8 times 10 to the negative 5th. And then we are going to set that over X times X, which would be X squared. Okay. And then over our concentration of NH3, which is going to be 15 minus X. Okay, so now we have that set up. So what's the next thing we have to do though, Drew?
Gotta solve for it. So like
Solve. We got to do some algebra. Okay. So if we take a look, our equilibrium constant is pretty small. It's to the negative 5th. As long as it is to the -3 or bigger for that exponent, meaning like more negative than that, we can assume 0. Because KB is small. Okay, so that helps us out significantly in terms of math. So what we'll do is we'll cross multiply. So it becomes 1.8 times 10 to the -5th times 15. Which comes out to 2.7 times 10 to the -4th. And that equals now x squared. So to undo that, we're going to take the square root of both sides. Okay. So if I take the square root of my value, x is going to equal 1.6 times 10 to the -2nd. Okay, so now I have my x value. What does the x value equal, Pamela? What does that represent? What is that the concentration of?
Wouldn't it be the concentration of H
Not H.
and H?
So if we look up here, it would be the concentration of NH4 plus. Yep. What else is it the concentration of?
OH minus.
Yeah. So this is going to equal the concentration of our OH minus. Okay. So now we have a concentration of OH minus. And we want to get to pH is our final end goal, right? We're going to get to pH. So Pamela, what am I going to do? What's going to be my first step?
We're going to want to set negative log.
Mm-hmm.
And then the concentration of 1.6 times 10 to the -2.
Uh-huh. What is that going to equal? Not the number, but like, what is that the value of?
POH.
Yes, POH. So we're just going to plop that into our calculator. So I've got it still in my calculator. So negative log, second answer. So we end up with 1.78 roughly is our POH. But we want the final answer of a pH. So what are we going to need to do for that last and final step?
We're going to have to get 14 minus 1.78, which will get us to the pH.
Yeah, so 14 minus 1.78. Which gives us 12.22 for my pH. And there's our final answer. Okay. Any questions about how to do these? Notice that it's almost identical to what we were doing with our weak acid. The only problem, or the only difference is the concentration that we get is not of H plus, but it's of OH minus. And because it's of OH minus, we have to do this little added step at the end to go from POH to pH. Good. Thanks, Pamela. You did a great job there at the end.
Miss,
Yeah.
I wondered why is it 14? Like, why 14?
Okay, so here's the other thing. It's only 14 if this is at standard conditions, so at 25 degrees Celsius. And the reason for that is because our KW for water at 25 degrees Celsius, which is, again, standard conditions, is 1.0 times 10 to the -14th, which equals the concentration of H plus times the concentration of OH minus. So if we convert all of these to pKw and pH and pOH, that makes this, instead of times 10 to the negative 14th, that would be 14 is equal to pH plus pOH. If we take the negative log of this entire equation. So that's where the 14 comes from. If we had a temperature other than 25 degrees Celsius, then it would be whatever the negative log of that kW would be what you'd set it equal to. Does that make sense, Almi?
Yeah.
Yeah, so that's where it comes from. The chances of them ever giving you a non-standard situation in terms of finding pH are slim to none. And then the 14, you don't necessarily have to have memorized. It is on your equation sheet for the AP exam. It's right there. Okay. Let's try another one. With these, the more you do them, the better you're going to get at them. So let's get at another one. So this one, we have a solution of methylamine, and it's a 1 molar solution of methylamine. We have the Kb for the methylamine, which is 4.38 times 10 to the negative 4th. So let's run through all the steps that we need to do again to make this happen. So Annika, what's the very first thing that we need to do?
Write the dissociation equation.
Yep, and what's that going to look like?
CH3NH2 plus H2O will turn into, it'd be CH3NH3 plus OH minus.
Yep, NH3, that would be positive because it would have an extra hydrogen on there. And then plus OH minus, absolutely. And again, the reason we get that OH minus is because the hydrogen from the water is going to be transferred to the methylamine. Good. So that will be our dissociation equation. Remember that water is a liquid. The rest of this stuff is aqueous. That's why the water is not included in our equilibrium expression. Speaking of equilibrium expression, that's going to be our next step. Okay. I know I keep calling you on this, Connor, but I want to make sure you got it now. So what would be our equilibrium expression?
It's CH3NH3.
What is it going to be equal to? Because that's
KB.
Yep, KB is equal to what?
CH3NH3. And then the concentration of OH.
CH3NH3. Don't forget the charge. That's positive. Concentration times the concentration of what?
OH negative.
Yep.
And then it's over CH3NH2.
Yeah, so over the concentration of CH3 and H2, we're good to go. All right, so that was step number 2. We just took care of that. So where do we go from here? What's our next step that we need to follow? Pamela, what's next?
We'll have to do the ICE table.
Yeah, and how would I set up the ICE table? What would I do? What's going to be my initial?
So for the initial, we're going to need 1.0 mole.
Molar. Good.
Molar. And then for the other ones, we're going to cross out H2O.
Why do we cross out H2O?
Because there's, I don't know.
Is it part of our equilibrium expression down below?
Oh, no, it's not.
No. Why is it not part of our equilibrium expression? What state of matter is it?
Liquid.
Liquid. And we don't put liquids or solids into our equilibrium expressions, so we don't need to worry about them in our ICE table. Okay, good. All right, and then what are we going to have for the concentrations of these two?
We would have a concentration, so it would be 0, 0.
Yeah. Why don't we have any concentration initially?
Because it didn't state nothing in the thing.
Have we had any dissociation yet? If this is initial, has anything like separated initially?
No.
No. So that's why these are 0. So initially we have no dissociation, which is why we don't have any of these to begin with. Good. What is my change line going to look like?
Minus X.
Mm-hmm. What about this one?
And then, X and X.
Good. Why is it minus X over here, but plus X over here?
Well, it's the product side.
So this is the reactant side. So why on the reactant side is it minus?
Because it's being dissociated to the other side, the product side.
Yeah, so this is being used up, it's being dissociated, so we're subtracting from this side, and then we add to this side because we're making these ions. Perfect. So then what's going to be my equilibrium line? What do I got going on there?
It would be 1.0 minus X.
Mm-hmm.
And then for the other ones, it would just be X and X.
Mm-hmm. Perfect. Okay, so we got that going on for us. What is going to be our next step? What do we have to do after this? Emily Augustine, what am I doing after this step?
Write it into our equilibrium expression.
Yeah, so we're going to throw that into our equilibrium expression. So we have our KB is right here, so 4.38. And what is that going to be equal to? What are we going to be writing for that, Emily?
At the top, x squared.
Mm-hmm.
And then at the bottom, 1.0 minus x.
Perfect. Okay. So this still meets our tolerance because it's to the -4th. So as long as it's above to the -3, we're good. So what are we going to do with this x here?
Assume it's 0
Mm-hmm.
because k is small.
Yeah. Okay, good. Because again, by the time we round to 2 decimal places, because this is to the -4th, right? We're subtracting from 2 places further out. It's not going to be, it's going to get rounded away, that difference. So we can assume that that's approximately 1. So we'll solve through. So 4.38 times 10 to the -4th times 1 is going to be itself. Right? Because we're going to do cross multiply situation. And so that's going to end up equaling x squared. Take the square root of both sides. Okay, so square root of 4.38 to the -4th. X is going to be 0.021 roughly. So x, what does x equal, Lisa? What does that represent?
X equals the concentration of OH minus.
Mm-hmm. So if we want to get the pH, what are our next steps then, Lisa?
You're going to take the negative log of 0.021.
Okay, and what does that value represent? The negative log of 0.021.
That equals POH.
Yep. And so that's our POH. When I do that, that comes out to 1.68. And then to get to pH, what's the last step then, Lisa?
You take 14 minus 1.68.
Okay, so 14 minus 1.68, and we get 12.32 is equal to our pH, and that is our final answer. Good. Any questions about how to do that?
Will the pH ever be like small? Because like every time we do this, it's been like fairly big numbers. Like, will it ever be like 2?
So we're finding pH of a base, right? Of solution of a base. So
Yeah. Yep.
typically, if it's a basic solution, it's going to be pH greater than 7. If you have it mixed with an acid, then we could, if we had more acid in the solution than we had base, then we could end up with an acidic solution. So we'll talk about what happens when we mix acids and bases. That's coming up. Right now, this is just if I have a pure solution of a base in water, what is the pH going to be? So yeah, it should be 7 or greater because it's a base. But that's a good observation to see that pattern that these values have been big compared to the other day when we were doing pHs of acids. They were all small because we were looking at acids. Good. Last problem. So it tells us the pH. So this is going to be a problem where we're going to have to work our way backward, right? It says a solution of triethylamine has a pH of 1.55. Find its initial concentration. So we're going to have to work our way a little bit backward, right? So how are we going to do this? What might be our first step? Emily, what do you think the first step is? Emily Gustin.
Do the 14 minus pH equals POH.
Yeah, okay, so 14 minus pH, because it gave us a pH right here. So 14 minus our pH, which is 11.55, will give us our POH. So that would equal 14 minus 11.55. So that's a POH equal to 2.45. So Emily, why'd you do that? What's your next move?
To convert the POH to the concentration of OH minus.
Yeah, absolutely. So what this is going to allow us to do is now that we have POH, we can go to concentration of OH. So how would you do that, Emily?
Would it be 10 to the power negative 2.45?
Yes, ma'am. That's exactly what we would do. So 10 raised to the negative POH will give us our concentration of OH minus. So 10 raised to the negative 2.45. So that's going to give us a concentration of 0.0035. 5. Okay, so we have concentration of OH minus. So what does that tell us? What does that allow us to do? So Emily got us pretty far. She got us to the concentration of OH minus. So Annika, what do you think would be our next move?
To set up an ice table?
Okay, so we could look at the ice table. So triethylamine, that's a long formula. So I'm just going to use B to represent base, okay? So let's just do a generic equation. So we would have base plus water. Okay, so the B just represents this triethylamine. So base plus water is going to give us BH plus, right? So the hydrogen is going to be transferred to the base. And then we'd end up with OH minus, okay? So this is just a generic equation anytime you have a weak base. So base, the hydrogen is going to go with it. We're going to get BH plus because the hydrogen is going to connect to the base. And then we're going to get OH minus, okay? Yeah, so we've got that, and we're going to set up an ice table. So Talk me through that idea. Why are we setting up an ice table, Annika? What are we going to do with that?
Because you know the concentration at equilibrium, so you need to find the initial.
Okay, so initial change equilibrium. We don't care about the water because it's a liquid. And we know that these started out initially as 0. We know that that's going to be x. And do we know what x is, Annika?
X is our concentration of OH minus, the 0.00355.
Yeah, so this x is going to equal this number up here, okay? So we have our x values. And so if we want to know what the initial was, this is minus x. So it's going to be our initial minus x. We're going to have to do some solving. So in addition to doing the ice table, what's the other thing we're going to need to set up, Annika?
The equilibrium expression.
Yeah, we're going to need an equilibrium expression. Okay, so the next thing we're going to do is set up an equilibrium expression. Emily Krulikowski, what is that going to look like?
That would be Kb equals the concentration of BH plus times the concentration of OH negative all over B.
Perfect. Okay. So we know these two numbers because those two numbers are equal to that number there. And then the bottom number we know is going to be something minus this number. And we know Kb because that's given to us right up here. So what we would do is 4.0 times 10 to the negative 4 is equal to, so these values are both the same. So I'm just going to do 0.00355, and I'm going to write that as squared. And then on the bottom is going to be some value, concentration base, minus this value here. Okay, so what that means is we're going to have to do some algebra. So we start off by cross multiplying. So it would be 4.0 times 10 to the negative 4 B minus, so we'd multiply these two together. So 4 second E negative 4 times 0.00355. Okay. And then that's going to equal this value squared. And that's to the negative 5th there. So now we have to rearrange. So I'm going to add this value to both sides. So we would get 4.0 times 10 to the negative 4th B is equal to 1.40 times 10 to the negative 5th. And then we divide both sides by 4.0 times 10 to the negative 4th. This is all just straight algebra, friends. Okay. Let's do that right. 1.26 second E negative 5 plus 1.42 Can be -6. Yep. Okay. And then divided by 4.0 to the -4th. And when we're all said and done, that means that the initial concentration, the concentration of B initially is 0.035 molar. And there's our final answer after all of that work. So just so you guys know, chemistry class, algebra class. So this bit down here is just straight up, do you remember how to rearrange equations and do some algebra to get our final answer, which is 0.035. Look at that, guys. 1 minute to spare. That never happens. So what you guys have for homework is some calculations dealing with pH and weak bases. You also have your take-home quiz. So your take-home quiz is going to be over problem sets 1, 2, and 3. Okay. So that's going to be also your take-home that you're going to work on as well. Any questions? Anything I can help you guys with? For those of you who have been showing up on Tuesdays and Thursdays, thank you so much. That is going to be the only way we're going to be able to get through all of the content in time for the AP exam on the 25th of May. So please keep coming to those sessions. And if you can't make them, I'll continue to record them. So I'll see you guys. Have a fantastic weekend. We just have one last little hard push to get to May 25th. Once we're there, smooth sailing. Okay, guys. See you later.